All right, everybody got enough caffeine to make it through the rest of the day?
Home strategy.
Home strategy. All right, well, good afternoon. My name is Eric Busboom, and I'm the founder and director of the San Diego Regional Data Library. We are a new nonprofit that's helping social and civic organizations, governments, nonprofits get data they need. And today I'm going to be talking about crime and census data. Mostly about crime data, that's where we're doing most of the work. The census data is coming along slowly since it's very difficult to work with in a general way. We'll talk a little bit about that. So if you want to get this presentation, it's got lots of pretty pictures in it. That's mostly what it is. You can go to our website at sandiegodata.org. The first post is about this presentation. And along with all the other stuff that we've got available, including our data repository and a lot of other interesting tidbits about crime analysis. So most of what we're doing today is a very visual presentation. It's talking about pretty maps. I think this is gorgeous. It kind of may not be entirely clear what it is, but there's all sorts of wonderful stuff. This is downtown San Diego crime points. So we'll get to that by the end. Talk about how we got to that using Python. So we are working with a wide variety of data. Since we're just getting started, we're starting to collect data sets and figuring out what's available, and in particular processing them to make them more useful. So there's a lot of ways where if you go out and get data from Sandag or you get data from Sangis, you'll find that you can work with it, but it's very hard. And if you don't have a lot of data skill, which is the folks that we're particularly catering to, there's a lot of processing required to do that. So we're figuring out what do people need to do, what do they need to, questions do they want to answer with data, and then helping them get that information by reprocessing a lot of this. So we took this as another crime map, a heat map. This was generated from data that actually came from Baltimore. I mean, it's San Diego data, but I had to go to a guy in Baltimore to get it. Showing a couple of the hotspots in San Diego. We're working, there's a violent crime hotspot. It seems to be a motorcycle training center in Kearny Mesa, but we do a lot of heat mapping to look out for where are these areas that have above average crime rates. We're going to be incorporating street lamp data. This is a heat map of how well lit are various streets with regard to where are the street lamps. We're not using wattage of street lamps, just the existence of them. They'll figure prominently in the crime analysis.
What's the hotspot there?
Let's see.
It's your house.
Yeah, that I know.
I seriously used to live right there. I think.
Yeah, I don't know. I found a bunch of them. I didn't even realize this. My part of Pacific Beach is the best well-lit area in the Pacific Beach residence. I had no idea until I saw the maps. Then as I go out, I realized, well, I'll be damned. We do have 3 street lamps per block where everybody else has 1. I had no idea until I saw the maps. I haven't been down there, so I'm not real sure what that is. This might be Horton Plaza right down here. So it'd be the park just north of Horton Plaza. Alcohol permits. We're starting to process alcohol permit data. As you wouldn't be too surprised, most of the crime in San Diego is related to where do people go late at night to gather to drink alcohol. And so alcohol permits are strongly correlated. The alcohol permit data, however, you can get this map. This comes right off of the ABC website, the Alcohol Beverage Control website. When you download the data, these are addresses. They're not latitude and longitude. So if you've got a GIS program, you can't do anything with it until you geocode it. So that's one of the things that we need to do is be able to geocode this and then connect it to the businesses that are in that area to produce crime maps. Here's a population density map. This is pretty much the extent of where we're working with census data right now. Census data is enormous. It's the full 2010 census will take up about a terabyte when you finally process all of it. Each of the 7 segments runs about, the largest one runs about 120 gig. This is a case where we've taken the population of every census block and plotted on a map. This isn't too hard to do. You'll find other places to do this, but we've done it in a fairly general way that allows us to apply any census variable to maps like this. And the next step will be to turn this into a regular heat map on a square grid rather than the blocky shapes that the census uses. And I'll mention a little bit why we want to do that later. So that's the kind of stuff that we're doing. Here's the tools we're using. I'll give you a brief overview. A lot of the stuff we've already seen, Python, obviously. A lot of our geographic work is done in GDAL and OGR, which are a Python, it's a C++ library with Python bindings. A lot of numping. We do HDF through the H5Py library. If you do Anaconda or one of the other scientific libraries, you'll get that automatically. It's a structured data format for basically storing NumPy arrays or array data. PETL is, ETL stands for Exchange, Transform, Load. It's a business warehousing or business intelligence data warehousing library, but it's good for transforming from one structured set to another, doing transformations in the middle. And then all of our data is SQLite. Everything we do starts with a SQLite database and ends up in a SQLite database, and I'll mention a little bit about why that's such a powerful way to do this. And Drew, you should be you should be doing IPython Notebook. It's really amazing. This is, and then Matplotlib is for our exploratory analysis. So the crux of what we do beyond Python is these two libraries are strongly related. They're basically tied together in the same websites. There are C++ libraries for doing raster libraries, which is basically just an image that's georeferenced, so you know what the latitude and longitude of Earth pixel is. That's GDAL. And then OGR is a feature library that deals with the points and lines and shapes and areas. So in this image, these colors, the heat map is a raster. In that particular case, originally we had squares which were 1/5000th of a degree. In this case, they're 20 meters squared per pixel. And GDAL allows you to make those associations between pixel and area on the ground. And then OGR lets us do the contours, the shapes, boxes. It lets us deal with road networks, finding out where's a road and what are all the points on the road, where are addresses, all those types of things that show up in a shape file we do through OGR. And then, as I mentioned before, everything we do goes through SQLite. Is there people familiar with SQLite 3? This is one of the most wonderful tools anywhere. It's by far the world's most widely deployed database, probably by a factor of 100. Every one of your phones has it. Every one of your computers has got multiple copies of it. It's in HTML5. I don't know if they finished the web storage, but it's spec for that. Every copy of every Macintosh has got it. It's a single file database. It allows us to store structured data, and not only store the structured data in a nice structured way, which you can do with other libraries, but it's a full SQL implementation. So when you open up a file, you can start to do queries on it immediately. It's powerful enough you can run a whole website on it. A lot of Python programs, particularly Django, will work with SQLite just as well as will work with MySQL or Postgres. So you can run your entire website off of that. Concurrency is terrible, but for this kind of stuff, it actually compresses better than CSV. So we load files into this. We take them out of CSV, stick them in SQLite, and then can run queries on them, and the files are actually quite a bit smaller than if we'd done it with CSV. And the documentation has these cool railroad diagrams that the guy who developed this, the one guy, does himself, so that's kind of fun.
How is it compared to GZ CSV?
It's very, very good because in fact, it is quite small. If you gzip both files, the SQLite file will be smaller because when it stores a number, it doesn't store it as text, it stores it as a number. And it also does it with dates. So your date strings in a CSV will be quite long, whereas they'll be at most 8 bytes or whatever. I think it does 64-bit for date. So it does a really, really good job. There's no commas, there's no quotes, none of that stuff. It compresses it down really well. So here's an example. This is one of our files right here. This is the Spot Crime US Crime Incidents that we've got our own bundle strategy for packaging data that I'm not describing here. But this is the California incidents. And you can open the thing up in SQLite and then run a query on it and get all the information out. And that's we do that within code as well, so that when you're transforming one set of data into another, you can use the SQL to do that.
Can you download the data in the SQLite database? Or?
Yeah, with our system, the bundles code, that is a whole other presentation, a much longer one by the way. You've got a management interface where you can request specific data. You can search for data. It's like a package format. It's like Debian or apt-get for data. You go search for crime data, you'll get a list of crime data. When you say go get it, it loads that SQL file on your machine. And then the step that is coming next with that is you can tell those a set of SQL files that you want to manage a relational database with. So you can say, give me all this data. It'll deal with dependencies between data sets, because sometimes there are dependencies, and then you can configuration control a relational database and then work your all of your data analysis off that database. So HDF5 is another really good tool for structured data. This is more or less like a structured file system in a single file for NumPy. It doesn't really, the base C library doesn't use NumPy, of course, but it has that concept of multi-dimensional array data. It'll do both indexed arrays with numbers. You can also do structured formats where you've got names for the columns. You can do objects. It allows you to store metadata for each of these things. And it's built for absolutely enormous files. So if you've got 100 gigabytes of weather data, you can stick it in this, break it up in parts, and send it to somebody, and they can still use it. Platform independent. We do it for the crime data. It's an intermediate format for transferring between processes. We don't use it quite as much as SQLite, but it compresses better and it's a lot faster. Partly because when you store data in, particularly with H5Py, when you load it back up, it comes into a NumPy array. You have to do the little colon bracket trick to have it come back as NumPy, but you can use all the NumPy stuff with it after that. So it's really, really efficient, very easy to program too. Then of course, IPython Notebook. Got a couple Gaussians that we'll talk about in a minute. This is one of the most wonderful projects ever for being able to explore data. We don't use it as a normal course of the day, but it comes up a lot when you're trying to figure out what the heck's going on with something. So we're going to talk a little, I'll walk you through building one of those maps and some of the stages we use and what the processes are. You'll have to go find this data, and the data you can find at data.sandiegodata.org. It's right in our data repository. So this is all coming out of another tool that I use on a constant basis, which is QGIS. If you want to do anything geographic, if you want to look at anything in a spatial relationships, get QGIS. It's a C++ program, but it integrates Python very well. It's free, it works great. It's got a couple glitches here and there, but for the most part, anything you want to do with free GIS tools is fantastic. And it also, with a plugin, gives you the Stamen maps. These are wonderful maps for analysis because they're very plain. They don't, if you put Google hybrid maps behind, there's all this clutter with names and things you really don't need. So here I've taken the crime incident points that I got from Sandag. For 2012, we did a bunch of processing to geocode them. And as I mentioned, we didn't geocode them very well. These things right here, these two squares right here are geocoding errors, some very bizarre geocoding errors, so we had to fix that. Geocoding turned out to be very difficult. I spent a couple days just writing an address parser to try to parse street addresses, and then you go geocode, because when you're geocoding 1,000,000 points, it's really slow. 1,000,000 points using a Google geocoder, the free Google geocoder, would take me several months to geocode because they only give you 2,500 a day. If you wanted to pay for it, it's about $800 to $1,000 if you want the good geocode. So this is a lot of programming to make this work. So we got the crime points, we stuck them on the map. And what you're kind of interested in here, this is a pin map. Which people have been doing since the 1800s. We want to know more about where is the hotspots, where are the areas that we should be analyzing independently as a cohesive place of high crime. So let me do that. So we take these points, we generate a heat map. You've all probably seen a heat map. They're not terribly difficult to generate, but we'll show you how we do it. And that relies on a Gaussian kernel estimation function, which is a fancy name. It's really quite easy. So this is a Gaussian distribution in 3D. It's if you cut that down the middle, you'd see a little nice normal curve. This is what it looks like in NumPy when you do it or plot it in Matplotlib, the 5x5 square with a high value right in the middle. The way that we build these maps is essentially as if you took like a big pile of sand and you dropped it on the ground. It makes this nice Gaussian shape structure for every point. And as you add them up, it's just an additive process. Every time there's a crime point, we drop this Gaussian onto an image, and they add up. And eventually you get a heat map. Very simple. It's called a kernel. And it's very similar to how you can build what are essentially histograms from discrete data that doesn't have a continuous structure to it. And we've got our own way of doing these kernels. They're always odd shapes, so you've got one point in the center. If you don't have one point in the center of the map, it's a little wacky. and the rest of it's all numpy where you can go iterate over all of your points. We have to translate latitude and longitude. Our points come in lat and long, and then we have to translate them to a state plane grid, which is a meter. So latitude and longitude are polar coordinates. We want them in distance because I want to make sure that every pixel is 20 by 20. If you make your pixels, say, originally was 5,000th of a degree by 5,000th degree, they actually end up being rectangular. It's 18 meters by 22 meters because the Earth isn't round. You know what? It isn't flat. It isn't even round. So there's a lot of math that has to go on using GDAL and OGR to make these transformations. And then the apply just drops those points on the grid and adds them up. And what you get is this heat map behind. Next step is to go figure out, well, where are these hot spots? Where are the areas that we should be looking at? And the way you do that is by finding contours. There's a lot of, if you go to SciPy, there's a whole section of SciPy that's dedicated to finding clusters. It does all sorts of crazy stuff, like going through all the connections between all possible points and finding minimum distances and trying to group them together. We said, oh, to hell with all that. I'm just going to draw a line around the spots that have that are large on our heat map. So in GDAL, you can say, go draw me some lines on a heat map. I want things spaced out from the minimum to maximum every values of 10 or every 10th of a percent or whatever it is. And these lines are actual vector lines overlaid on top of a heat map, which is a raster. Then next step is we go say, just give me the ones that are in the 95th percentile, so type top 5%, draw a box around them. That box, you can kind of see that there's this, it's probably this one right here, plus a little bit of buffer, that puts the box around. This area doesn't illustrate it very well, but there's lots of little boxes. There's one here, there's one up there. In North Park, there's lots of little ones that will show up all over. So then we go back into GDAL and ask GDAL, show me for this box all the boxes that are close to it. Let's combine them together. So I take those two boxes and I put them together and I say, okay, now give me the box that goes around it. That's the purple one. Eventually, the system settles down and stops combining boxes, and what you end up with are these square areas that fit around neighborhoods, which are high crime areas. And that's useful because doing a geographic search on a shape, you can install stuff into Postgres, you can install extra libraries into SQLite and do geographic searches, but they're very expensive. If you do it in a square area, I just say anything between this latitude and that longitude, give it back to me in a SQL query, and I can do that very quickly. It turns out, though, and this is the odd part, is that this box is square in meters. It is not square in latitude and longitude. It's got a kind of a curved shape to it. So there's all sorts of wacky stuff when you're moving between meter references and latitude and longitude references. But fortunately, the libraries handle quite a lot of that. So now from this point, what we do is we'll go back. We give this thing a name. This is gas lamp. We got North Park. There's one for Pacific Beach. There's a bunch of these named areas. And we do time series analysis on those named areas, on just the points that are in there. What turns out is that there's a lot of descriptive statistics of each of these areas that's different from area to area. The peak of crime in downtown is different from the peak of crime in North Park at time of day. That's valuable when you want to figure out where you park your cop car and get to the next crime. So we're going to be soon incorporating population statistics. This is another major GDAL and OGR process. We went to the census. We downloaded all the shape files for each of these city blocks. They have a little shape for every block. We told OGR, I want this block to have value 5 or 10 or 15. In this case, it's how many people live in there. Divide it by the area of that block, and then have it rasterized into another map. Now, this map is a bit of a problem because it's not square. The boxes aren't all square. It's not regular. So some of them are going this way, and some of them are going that way, and some are all wacky shapes. Your brain doesn't integrate those very well. If you look at the previous ones where you've got a nice heat map, they look sensible and natural. They kind of feel organic. This one feels just jarring and wacky, and it's hard to interpret. So we're going to turn those into heat maps as well. That turns out to be a really complicated process, but the result of it is a much easier map to interpret. And then we'll be taking this information from this map. You can kind of tell where the businesses are because there's no people there. Most of the time, sometimes people live above the business and that doesn't work out well. But you can use this to figure out things like adjusting for the prevalence of car theft or burglaries so that you can understand how does population or lack of population affect crime statistics. There's a lot more to those things than that, but that's a kind of an overview of where we're headed. Very broad involvement with Python. And if you want the presentation, that's the site. If you want to participate in one of these projects, we'd be looking for analysts to, one, do some of the descriptive analysis. We'll give you all the data, give you some ideas about where to go, and then you can go find out some interesting stuff. There's a lot of neat little tricks and clues and bizarre corners in the data that's kind of fun to look at. We'll also, working with Brent, we'll be working on setting up a Kaggle predictive analytics competition probably in the fall, where it'll be a contest to try to figure out where do you put the cop car to reduce the travel time to the next crime. If you'd like to participate in that, you should sign up on one of our lists, and we'll let you know how to be an amateur crime analyst. All right, well, thank you. Any questions? All right, well,
What do you want to do with the company? Do you want to?
What's that?
What do you want to do with the company? Do you want to get hired by the city or anything? Or?
Well, this is a nonprofit, so this is going to be a nonprofit. Well, I have a company that's kind of on hiatus right now while I figure out what the opportunity is. My hunch is that when we get into municipal data, which is just starting to open up, that there are a lot of business opportunities. I don't know quite what they are yet because the municipal data is still pretty closed, but we're working on opening a lot of that up. So another question? All right, fantastic. Thanks.